right. Hello, everyone. Let's get started. Yeah. All right, we're going to get started. So a few things. We're currently on week 12, so that means we have exam. No, we're week 11, right? No, week 11. So the exam 2 is next week, right? Right? All right, so it's going to be the second half of class next week. The exam is comprehensive, so anything we've covered from the beginning of the semester until now, until today. It's closed notes, but you're allowed your cheat sheet. So same format. You can write whatever you want on that cheat sheet. Got it? All right. Any questions about the exam? Exam 2? Nope. All right, great. Second thing, the term project. So we have about 6 weeks or less, four maybe, weeks left in the semester. So I think we talked about this already, right? So make sure you form groups of 2 or 3 and just pick a topic. Send me an email, please. 1 per group, just kind of like maybe 2 options of what you want to do for your project, what you're thinking about doing. The requirement is it should be deep learning and it should have transfer learning in it. Does that make sense? But otherwise, it's pretty open to whatever you want to do. You can do something with language. I know we haven't covered much with images. That's kind of what we're going to cover going forward. But, or it could be, whatever you want to, as long as it's deep learning and transfer learning. Make sense? Any questions about the project? So you have to do presentations the week before finals, right? So that's basically it. That week, that last day of class, essentially, you'll present your work, and then, of course, we'll have the final exam. Questions? As far as homework assignments, I think maybe there will be 1 more homework assignment that I'm thinking about. Maybe 2, but I think it'll just be 1. All right? All right, so please work on the project that's kind of like officially assigned. It's very open-ended. And then you should write a report. Obviously, you need to implement something and show evidence that it worked, but it's an experiment or some kind of a thing like that. Got it? All right. Then the next item is the homework, right? So you have a homework that's due tonight. How did that go? Solved it? He solved it. You solved it. You solved it too. Good. All right. Anything that we can publish? No. All right. So, but good. So you implemented the time series GPT. At least you had an idea of how that works, and you picked some time series data, right? I'm assuming. All right. So today, as I said, we were going to cover the RNN. I have a lot of notes on this one. We're going to take a look at it, and that's essentially it. So we covered. I think we should be able to finish the RNN. Hopefully, maybe not during the first half, but it's not going to take all 2 hours. Right, so, and as you can see, the next topic is we start the image sequence, which is going to be fast AI, stable diffusion. So I've already started preparing this lecture. This is probably one of the most complex algorithms you'll ever see in deep learning. So even harder a little bit than the transformer. This is actually what I'm thinking. The assignment, I don't know if you guys remember in 520 we did the CGAN. Do you remember the conditional GAN? So you can do a conditional stable diffusion. Do you see that? So, and that involves like attention. So essentially we're kind of putting together stable diffusion with a transformer. So the language part, although it would just be like, a 9 or an 8. So something very simple, like it was with the CGAN. Does this make sense? So that's what I'm thinking will be your homework assignment, okay? Just implementing that type of an algorithm. I have all the code for that. There's a lot of very interesting ideas here. So this is going to be a mix of some of the algorithms related to this, to image generation, images, and there's something called art style transfer, which I think is so interesting. And then the rest is just pretty easy. It's just going to be using the fast AI library, which fast AI allows you to bring in a ResNet and something like that. Got it? All right. And then I'll show you a few other things here and there. But that's kind of the semester. So today is just focusing on RNN, getting through with this algorithm. So obviously you've had an opportunity to look at what time series E is. You found maybe a time series data set, and you applied it with the GPT to try to create a time series GPT and measure some performance. Now we're going to look at the more classic algorithm, RNN, for sequence mining. This, as you know, initially before transformers, this was the technique that many people were using to try to solve language problems. So they were trying to do language translation with RNNs and so on, right? So this was definitely used for language. Now today I would say RNNs are used in more niche areas like sequence mining. So that's why I kind of have it here in this section. All right, so I have two links that I provided. One is the notes. I'm just going to go over the notes, honestly. They're very detailed, so we'll go through them, and then after that we'll implement the code. And the example that I have actually uses the familiar MNIST data set. So I'm just going to show you guys how we can use that you can use the RNN with that data, and you could use it for sequence mining or predicting a class or something like that. All right, so let's take a look here if there are no more questions. So this is recurrent neural networks, RNNs. As you can see, the architecture is this, you've had now time to think about time series problems. You understand the GPT problem, and it's the same one, right? So they're both trying to address the same issue. So you're going to have some kind of a sequence, which is a vector. It could be just one value, or it's a vector of 20. So that's your inputs x1, x2, x3, x4, all the way to x28. So you can see this one is already geared towards the MNIST data set, because MNIST is images that are 28 by 28. All right, so what happens is this is essentially a matrix multiplication right here. There's a weight matrix. So x times that gives you the next state, which is a hidden state, h1. You can see there's an arrow here, so you're going to have to initialize a vector here with random data or whatever you want to use. And then you have the x2 data, which would go in sequence, right? So like, whatever example you have, and that x2 would have its own weight matrix to create an H2, but here the issue is that H1 also feeds into H2. That's the sequence. That was usually the problem with RNNs. They needed to be sequential, whereas GPTs would not have this blue arrow here, right? Instead, the positioning would be encoded, like we did with positional encoding or something like that. But here, they were thinking more like humans and less like AI. And so this is how we think, so some kind of a sequence. All right, so here, and you can see this continues all the way to the end. And then after that, it just produces output vectors, so another matrix multiplication from this layer and a weight matrix to produce this Y vector. And of course, these are the things that you compare to the real data, so the predicted to the real. Okay, now here you can do lots of things with this. So you can actually use these values, or you could just take this H28. If you notice, this vector here has a lot of information of everything, right? So every X went into a hidden state that then goes into the next state, and it's essentially feeding into the last one. So this can become like the head, right? And then you can plug in something else in there for prediction. So the RNN is very versatile like that in PyTorch, so there's several things that you can grab from this architecture. But essentially you frame it this way and then you feed the data to it. So recurrent, RNN stand for recurrent neural networks. This is an important technique in deep learning that deals with sequence data mining and can be used also for classification and regression. So in my example today, we're essentially going to take an image, break it up into like the rows, and we're going to assume that you're kind of looking at the image from top to bottom, step by step. So you're like, all right, I see this. Okay, so the next one is probably like that, and like that. If it's a 7. So that's essentially what we're doing. We're assuming that we're looking at the image in parts, and then we're feeding that into the network sequentially. The network is going to learn these hidden states, and essentially we're going to learn something here, right? The goal is going to be that then this vector is going to predict just a class, or actually it's going to predict one of 10 classes because it's MNIST, so there's going to be a vector of 10 options. Does that make sense? So that's the idea. So essentially I have this capability to create these vectors, but I'm not using it. Okay? I'm only going to focus on this. So this is similar to when we did the BERT. If you remember, a lot of information went into the BERT, but we were ignoring pretty much everything that it was generating here, and we just focus on that very first embedding to say if it's, true or false. Remember? Next sentence, first sentence. It's the same idea. You can just use it that way. Okay? So this technique can be applied to images, text, and many other domains. So the only main difference with RNN's architecture is in arranging the data for sequence mining. Okay, so that's the challenge as usual. RNNs are well known for their use to solve NLP problems. However, since 2017, they have been overshadowed by the arrival of transformers and large language models. I remember a YouTube video I saw back then. I think I saw it in like 2019. And it said something like, it had a picture of a transformer from the cartoon in the 80s, and then it said something, RNNs are dead. And I remember seeing that back then, I was like, whatever. But it was true, right? So essentially RNNs were really important back then, and everyone was doing research, Andrus Karpathy, etc. They loved this technique, but it was really replaced by transformers. All right? So here's the main idea that we're going to explore. So something familiar, right? So we're all familiar with MNIST. So that's what we're going to look at. So using an RNN to classify MNIST. So for this example, I will use the MNIST dataset. The goal of the RNN will be to classify the images into one of the 10 classes, right? So in previous chapters or ideas in machine learning, we have treated each image as an example what does that say? Each image as a sample static in time of size 28 by 28, right? So this is how we treat regular machine learning. So we have an image, right, that is 28 by 28, is static. We spaghettify it into a vector of 784. It goes into the model, and we predict the class. Do you guys see that? Instead, now we're just going to take each row, and that becomes a vector in time from 0 to 28, and we feed that into the RNN. So yeah, so we usually we treat MNIST images as static in time of size 28 by 28, and we want to classify them as a digit. In the RNN, we will want to classify each image into one of the 10 digits. However, in the RNN, we will not treat each image as a vector of 784 features, or a tensor of size 28 by 28 if we were using a CNN. Instead, we will use a sequence modeling approach to classify the image. And that's the main idea. So here's the figure. This would be like the normal approach, but this is the way that we're going to treat it now with the RNN. So with the RNN, we will look at each image as a sequence of segments of the image or patches, a sequence in time. And then we use this sequence from beginning to end to predict the final class for the image. So essentially, we're going to take the image, break it up into the individual rows, 28 of them, each of size 28. They will go into the model to predict the class. Yeah, so it can be seen here that the 28 by 28 image is converted into 28 vectors of 28 features each. These vectors are fed sequentially into the model, and that's the main idea. Okay, so let's take a look here. All right, so I think that you guys get the idea. So I'm trying to see if there's another graph that's useful before we jump into the code. Right, so this is usually what you see in papers. You see something like this, so each X, and this is the sequence of hidden layers that you can have, because it doesn't just have to be one, right? So here, even though I only have one, think about it. This can be deeper. Do you see what I mean? So it could be one and another one and another one until the Y. So that's possible. So that's what this represents. And yeah, that's the same. So I've shown you this. Yeah, all right, so those are the graphs I have. So we can jump now, so read through this, but it might be easier just to go through the code and kind of get a feel for it. So RNN code. Okay. All right, so I'm not gonna spend too much time on RNNs. There's several variants of them. There's the plain vanilla RNN. That's the one I'll cover in class. There's one that's considered to be more advanced, and it's called an LSTM. It stands for short-term memory, long short-term memory, I think it is. And so this one, it may be more powerful, but it uses a special type of a neuron called the LSTM neuron, and so on, right? So it just goes. It's more. There's more to it. So today we're just going to focus, and in this class we're just going to focus on the first one, the simplest one, which is this one. Okay, so let's start playing with it. All right, so I'm going to open up Colab. New notebook. I'm going to use the MNIST data set for this. Okay, so just double check here. Yeah, so first RNN, MNIST, so simple recurrent neural network for MNIST. We want to predict the class per image that is 28 by 28. We are going to think of each image as a sequence of rows. Therefore, and this is important, you have 28 rows of 28 pixels each. All right, so let's start. Okay, so we're going to use Torch Vision for this one. NumPy, just for a few functions, matplotlib, pandas, pill image. Okay. A few libraries from sklearn also. Give it a minute. Okay, good. So RNNs are not really my favorite neural network, I'll be honest with you guys. I've always thought they were just too convoluted, but so what I will do first is we're just going to play with random data, okay, just kind of get a feel for the shapes and things like that, and then we're going to build the network. All right, so let's add torch, torch utils, optim, torch nn, torch functional, torch autograd, so the same variables. So the key with RNNs, honestly, is keeping that mental model of what you're building and then looking at the shapes as you're building it. So yeah, so this is where the algorithm would start. Basic RNN, main loop, core functions. But let's start here, all right? A very simple RNN basic simple example just so that we understand what's going on. So I'm just going to create simple constructs here. So let's start with this one. So you have to define a lot of parameters with RNN. So you specify, so for instance, there's an object called nn.rnn, right? And I can create a variable. Here you specify the number of layers, the hidden size, and the vector size. Do you see? So that's the idea that I was saying. You can have 2 hidden layers of 20, and so we can do that. You see that? So this is how you start creating it, putting it together. Here we can create, so for instance, some data that we're going to use. So I'm just creating random data here. So notice torch random. I'm going to specify, and I've used different numbers here just to kind of keep it simple or visual. So sequence length, batch size, vector size. If you notice, this is similar to the GPT, actually the exact same thing, but 2 of them are inverted. This is something that PyTorch, for some reason, had in the past. It would create RNNs in this fashion. Later on, this has been fixed, so there's another approach that now considers, like the GPT, because this should be, this is how we did the GPT, right? So batch size, then followed by sequence length, followed by whatever the vector size was, right? So vector size. Do you see that? So just to give you the context in the GPT, what was the batch size usually? Was it 64? 64, right? And then what was the sequence length in the 2017 paper? 40. Do you see that? And then once this is embedded, what was it? 512. Do you guys see that? That's essentially what we're doing. Okay? The same thing, because you would have batches just means we have more than one example, and I think it's going to be useful for me to have this open. Yeah, this. So batches just means that we would have 64 of these sequences. Sequence length, 40 or 28. And then the size of this vector, whatever it is, So that's kind of the idea that we have here. All right? But, and this is the PyTorch can accept a tensor like this, but originally they would encode it kind of the sequence first, then the batch size, then the vector size. So this is how I have it in this example. Just be aware of that. Okay? All right. So here's an example where I have then a sequence of 5, a batch size of 3, and then I have a vector size of 10. And if we want to connect this to our example that we will do with MNIST, obviously the sequence is 28. The batch size, I'll have 1,000 images, and each image is a vector of 28. Do you guys see that? And so we're feeding in the images, and our goal is, we're not trying to predict for every row in the image, let's say like a class or something. We're just going to encode all that information so that we get to a final hidden layer, and then that final hidden layer can be used to predict something like a class. And if as I said, if that confuses you, just remember the BERT score. It's exactly the same principle, right? Because we can shape the weights to go to any direction that we want. So for instance, we just want the whole focus to be on that last hidden layer, for instance, because that's what's going to be evaluated. We predict, we compare to real, we backpropagate. So that's the idea. Make sense? All right. So that's the data there. Some torch random. did I not? When I ran these. Okay, let's try this again. Okay, there we are. So we have our tensor data, and then essentially the data. Oh yeah, go ahead.
And this is probably a real simple thing that I'm missing. But when we were looking at the data imaging earlier, I understood like the vector of 720, because we were looking at, essentially the brightness of each pixel, right?
Yeah.
How are we doing that? If we're not doing that here, if we're not spaghettifying that,
Mm-hmm.
how is the computer understanding of the images?
Yeah, so no, it's a good question, right? So it goes to the way neural networks work. So this is okay, so the image, right?
Yeah.
Is 28 by 28. So you agree each vector is 28 and there's 28 of them. So that's an image. I just grabbed the first row, the second, the third. All right. But I'm going to feed it in a different way. Instead of just giving it all at once, I give it as a sequence.
Okay, so it's you're almost like the top line of pixels, then the next line of pixels. Then the next
That's
line.
right. That's right. That's
Okay,
right.
That's what I was missing. I'm sorry.
Yeah, so, and no, you're right. So let me go to the whiteboard. Right, so, an RNN is like a thing like this. This hidden layer depends on this one. And then this hidden layer depends on all the previous ones. But also, whatever it learns here, it's already encoded knowledge, and then that is fed into this one. And so this one uses that one, plus whatever else comes in, and that's encoded knowledge, right? So it's accumulating all this encoded knowledge. So then it goes ... to the last one. This is important because this is the end. But this one has all this encoded knowledge coming into it. So then you can, from each one of these, predict something because those are the preds. And those preds would then be compared to something that is real. So these would be the equivalent real data, for instance. So we could train it that way. You see that? That's definitely possible. Or we can train it in some other way, right? So now the key thing is now you have your image that is 28 by 28. So 1, 2, all the way to 28. So we cannot feed the image statically. Or I guess we could feed it into here or something, but the model actually is expecting, so these are the hidden layers. The model is set up that it needs something here, and something here, and something here, and something here. You see that? So all we have to do is kind of like, we have to like hit this to adapt it to this architecture. And so, well, if you want to do that for some reason, then you grab this one, and that becomes the input here. And I want to use a different color. That becomes that input. But this is a vector of 28 because remember this has 28. Then we grab this other one, and that becomes the input here. Do you see that? And then finally, we'll grab this one, and that becomes the input.
So it has all the learning from the previous 27 lines of pixels.
Well, you tell me, right? So this is the first one, right? The first one goes into H0. So this is a matrix multiplication of, this is a set of weights, right? So X times W produces this. And then guess what? This one goes into this one. So now what do you have? You're going to have another set of weights, this X times W, to produce like another H that you're not seeing here. And then that H and this H produce this one over here. So now it contains the information from this one and the information from this one. So it has captured the knowledge of this one into this one, and then this one goes into that one. So it is getting all the information. Yeah, go ahead.
And then that gets compared to what is the real data, the same input again.
So yeah, right. So now here is where the hidden model can predict this if it wants to. And it can predict this because this just depends on this one. So here we would have a set of weights, this times that to produce this, right? But we're not required to provide this. Do you see that? That's not a requirement. Instead, what we can do is, all right, if that's not a requirement, don't predict it. We have the capability to do it, but we just choose, in this example, not to do it. Now, if you had another time series problem, if you have that and that's your goal, use it. So now instead, this is why I was saying that this is similar to the BERT idea. So here you agree that all these rows of the image came in, right? And they're being encoded into the H's, and each H goes to the next one, and this H goes to this one. So all this knowledge here is not law. It's here, right? We haven't lost it. Okay? So then we get to the last one. This vector comes in here, times set of weights. It produces this layer, but this one also gets all the previous information from the x's and also in sequence. So now this becomes like the super block. This contains all the information, right? And now what do? Here we could potentially ignore that, right? Just extract this block. Essentially, think of if that makes it easier for you to understand, just extract that, because it's got information from all the previous ones, and this becomes like a head now. So now what do? Another set of weights, right? A matrix multiplication, and that produces a softmax vector of 10. And once we do that, we compare it to the real. So this is pred, this is real, size 10. Calculate the error, right? And what do we do with that error? We back propagate through the entire network. Yeah, go ahead. No, go ahead.
Where does the real one come from?
It's the class. So it's mness. In this example, it's going to be mness. So we're going to have an image that is 28 by 28, and then we just have that this is a 7, the label. So that's what I'm saying here is that, if we had something else, let's say we had another image, for instance, just to give you an example. Let's say that I had another image, that it's also maybe not 28 by 28, but just sequence of 28. So then I could learn from here to produce that other image in the same fashion. I would take this row and that becomes that. So it learns to predict that and we compare it. Do you see that? So we could train the model that way. And that's a sequential approach. But in this example, and that's how the BERT was, right? The BERT would produce, all the outputs. But we also learned that the BERT scorer, we could ignore all of them and just keep one. That's the same idea here. So I'm just, because it's mness and I have just the image and the label, I disregard these completely. All I care about is the accumulation of information until the last one. And then we just add some kind of I extracted this block, right, times a weights matrix, and that produces the vector of 10. So this is just a feed forward. So the dimensionality of this one, let's say that I make my hidden layer here 128. It's just a linear, right? NN dot linear from 128 to 10. Do you guys see that? And then that produces classes. Eventually they're random, right? You have to understand they're random. But during training, the weights get updated so that eventually the difference between predicted and real has to go down. So the question is, does it, can it be a good classifier? And as it turns out, it does a pretty good job. So do you guys see now, Matt?
Mhm.
Yeah, perfect. So yeah, no, great question, and that's what we're doing. So it's essentially, it has a lot of versatility, right? So we could predict sequences like this for sure. It just so happens that my data is not like that. So I'm just ignoring it and just predicting the class. Anything else, guys? Over there? All right. All right, so now that we understand this idea, if you guys want, with the data set that you use for your homework, then you could try to adapt it to this RNN, not as homework, but just as a fun exercise, right? So let's go back to here. Yeah, so I'll keep this open. All right, and right now I'm just kind of just giving you some of the tensor operations, then we're going to build it up. So this is the data. So you can see here you start to define the RNN and how it's going to work. Okay. So we did this one, that one. Batch size of 3. Oh yeah, this is the data, sorry. Okay. So we can create a tensor. So this is going to be the H0 that we're going to use to initialize our model needs to have something here probably, so we need to initialize something. So just a torch ran, for instance. So we can try that. Okay, so RNN basic, RNN here. And it's going to take the input and the initial hidden state. Okay, so you can see here it actually outputs two things also. Do you see that? So for instance, it outputs the actual hidden states or the outputs. We define that this is just so we define RNN basic to be an RNN, okay, vector size, hidden size, 2 layers. Okay, so now, all right, so we run the data through the RNN. We can print the shape. And it is 2, 3, 20. So let's take a look. So there's batches of 3. Trying to think. So yeah, hidden size is 20. There's 2 layers. The vector is 10. Sequence is 5. We have 3. Vector size 10, which probably needs to match that. So then there's definitely 3 samples, 2 layers, 20. Let's do output. This one is 5, which is 5. The sequence is 5, 3, and 20. Let's try another one because I'm kind of missing this one. Let's try this RNN here. All right, let's try. All right, this one is more similar to MNIST, so it might be more obvious. So batches 100, right? Okay, so we have 100 samples. And then I'm going to create data and batches. So this is going to be 100, 28 by 28. So I have 100 images that are 28 by 28. I will have to permute them because of the way that RNNs kind of encode this, right? Which is what I was saying. So permuting it now will make it 28 by 100 by 28. Do you guys see that? So I'm just flipping these. Okay, but it should be the first should be the sequence, and then the next one is the size of the vector. Okay. So now, hidden has shape n layers, batch size, RNN hidden size. And it produces and there's 0 initial state. So let's go with that. Let's take a look at this one. So hidden, 1 layer, n batches, RNN hidden size of 128. Okay. So 100. Okay, so this to me is the first hidden layer. Okay. Hidden RC. Now we create the RNN. So this one, what was that? N layers, it's got 1. This is what's tripping me up. So I'm thinking this is the 128 should be this. 128 should be the size of this one here. This should be 1, I think, or just 1 layer, and this should be then 28. That's what you need to define. So you just need to figure out like what are the parameters of your model, and you plug in those values. Do you see? So I have a data set, right? Because we started here. So I have one data set, 100 images. They're 28 by 28. Then I have, I permuted just so that that's how it wants it. And then this is just for the first hidden state, which this has to match to be 128. There's got to be 100 because there's 100 of them. And then here, this one, you specify that the hidden size is 128, just like this one. 28 is Oh, yeah. So 28 is, what was the first one? The vector, okay, the vector size. So that's the input. So this is like the input, right, size. Input size. Then this is the hidden one, so hidden. And I believe this is just that you only have one hidden layer. So number of layers. So 28, 128, only one of them. Does that make sense, guys? So this is how you define the architecture of it. And it's going to roll out by its own, essentially. So you don't have to like specify that sequence. Do you see that? So yeah, so let's put these numbers here. All right, so again, I'll repeat. So we have, so far we've established, for sure, we have 100 images. We created that. They're already 100, 28 by 28. We permute them because it needs to be 28, 100, 28. So we flip these two. Then we need to have an initial state, right, that we define, and that's just going to be, we have 100 of them, and the size is 128. Then we define the RNN, nn.rnn, so we specify almost like, okay, what's the input size? 28. What's the size of the hidden layer? 128, and we only have the one. Do you guys see that? And so that's essentially how it works. So that's RNN. We provide, so then now we can make a call to it. Okay. And it returns several things. So we do this one, RNN, then RNN, it takes in XB, that's the data, and it takes in the hidden layer, which is should be, you know, what comes in here. You need to have something which is just random. Okay, and then notice that it returns two things, right? So it returns the outputs themselves, or it returns a hidden layer that we can use further, right? So here, if I print RNN-O, there's 100 samples, 28. So that part. Okay, and then we have this hidden. Dot shape. $128. Right, so this implies it's got to be the last vector, right? So I believe that's the definition of it, that it uses the last one, because there's 100 of them, right? So 100 samples, but it's essentially would be returning this one for each of the 100, okay? So we'll see this when we implement the MNIST. And I'm ignoring completely the other one. So this we would have to figure out. It gave me a shape of 28, 100 by 128. So I get this. Obviously, it's the hidden state. It might just be giving me the whole thing, to be honest. So if you think about it, right? So it's giving me the sequence of 28 for each of the 100 samples and the hidden state. So it's essentially giving me all of these and all of these. And then I have to do something with that, which, you know, I didn't do. So I'm ignoring that. Okay, so now, so that's the shapes of this. So this is, you know, one of the things we'll need to use. So this is that printed both. Then drop out. Right, and then you can see actually, so let's just follow this logic. So it's showing that, imagine we're here, right? We can then take that vector and process it further. So you can see nn.dropout was just a dropout called droprc. Okay. Then what do we run through it? We can run RNNO, which is this part here that you can see that comes out of the RNN. So it's like we're giving it now a head, right? So, or something. So RNN goes into droprc, which just applies dropout, and it just produces RNNO shape. That should be the same size, right? So we just applied that to the network. Okay, then we have a fully connected layer. So I'm going to define a fully connected layer here. So this fully connected layer is just NN linear. It goes from 128 to 10. Do you see that? So this implies going from the last hidden of 128 to a vector of 10 over here, right, for the classification. So we define that fully connected. Okay, what do we run through it? So let's look at hidden RC again. So what was hidden RC? Remember, the RNN returns both the whole thing and just that vector, hidden RC. So we can take a look at the shape of it. Right, so it's for every sample a vector of 128. Okay, so now I'm going to apply fully connected to it. So it should be this one, right? So I just created fully connected. All right, so I'm going to grab hidden RC, and it becomes the input to fully connected. So that now I get out, and it should be then 100, 10. Do you see that, guys? And so what that implies is there's 100 test samples in the batch, but now it's producing vectors of 10. So it's exactly the idea that I was saying. So we could have used this, but I'm not using it at all. That's in that RNNO. You would need to add heads to it and all that. In this example, I'm just taking the image like this. It goes through this architecture. We take this guy here, which is 128, for each of the samples, because each of them needs to have a prediction. And then we put a fully connected head, this one here, so that now we have this output. All right. So that's why I started with this, because it's easier here to kind of figure out what the shapes are and everything, and how everything is going to fit in later when we implement the actual code. So here we can, because this is a dimension of 1, as you can see, we can just kind of get rid of that, like a squeeze operation. Okay, batch size X and output for 10 classes. So YPred, we have our YPreds now. And if we look now, YPred.shape is 100, 10. So more intuitive it becomes for every sample, the class. Do you see that? This is why I don't like RNNs. Okay, so because it's kind of like that, right? So you have to use your imagination to think, okay, this is the architecture. I need to fit it. So what is this parameter and that parameter that goes in this object that they've created? But yeah, because they created this RNN thing, and you just need to read what fits in there. All right. So we did this. RNNO. Okay, so let's actually look at RNNO a little bit more, although I'm not using it in this example. Okay, so RNNO shape. So RNNO, if you remember, was what came out of the RNN, right? So it gives you two things, or that. Okay. So says here that it's the sequence length, the batch size, which is pretty clear, and the hidden. Yeah. So essentially, right, this confirms what I was suspecting. So the sequence length and the hidden. So it's essentially giving you the whole thing. It's giving you 28, and it's giving you the hiddens. What's not giving you is the X's anymore. Do you guys see that? So essentially, actually, it's only giving you this part over here, which actually makes sense because this is now what you would plug in a linear on top of all of these to predict the value and so on. Okay, so that's what's happening there. So yeah, so actually pretty clear. Yeah, so you can see there's 28. There's 100 samples, there's 28 in sequence, and then it's just really, the information in there is, for every sample, is the sequence of 128 vectors. Okay? So we did that. Okay, so let's take a look at this one here. So in this one, because RNN is a sequence, right? For all 100 samples, I have a sequence of 28, but if I just do -1, it's just giving me the last one. Do you see that in the sequence? So that is now 100, 128, right? So it's giving me actually kind of the same thing. Do you agree? For every one, if we look at this one, we have the sequence of H's, but I just want the last one. So it just gave me that also. See that? So that's essentially the idea. It gives me the same thing. So this is how you play with this. You have to get into it and kind of, so the RNNs are like that. All right, let's take a look. So fully connected, RNN out temp. Oh yeah, and that you can see I'm doing the exact same thing I did over here. I'm just applying my fully connected layer so that it becomes of 10. The exact same thing. So it has a convenient way. So in conclusion, we can see that the RNN essentially gives you, where is it? The RNN gives you RNNO, yeah, here, right? It gives you the sequence for every sample of the produced hidden values. And you can either use all of them together or just the last one. You can see here, obviously we're going to have to put that head on here and predict something, right? And then what are we going to do when we predict? As usual with neural networks, we're going to compare it to the real value, calculate that error, back propagate. So just like we're going to do it with one, you could do it with all of them individually. Got it? All right, so that's the logic of the RNN. So now I think we're ready hopefully to implement the actual MNIST. All right, so that's done. So now let's go up. Take a look at this one too in a second. All right, so as you can see, it's going to perform really well, right? So you can see that the F1 score here is going to be like 96%. So Seems to be doing good. So let's implement it. Let's make sure we have the libraries. Learn. Okay, that one too. All right, so now the parameters. Now this is going to be specific to MNIST, so we're going to use the actual MNIST data set. It's a neural network, so learning rate 0.03. Batch size is going to be 1,000, given that this is MNIST 60,000 images for training. So batch size 1,000. We'll play with that. Number of epochs 20. Sequence length 28. Okay, remember it's every row. Size of vector, which is size of vector chunks per image. So that's that's actually the size of each row, right? Is 28. So it's 28. That's the sequence, and then each one is 28. Then RNN hidden size, that's going to be 128. So that's the size of these, the H's. So that's 128. And the number of classes for MNIST is 10. Okay, so good. So let's go ahead now. Let's bring in the data set. So train set first. Okay. Then the test set. Okay, so here, I don't know if you guys remember these. So these are the transforms that we can use sometimes with data sets. So essentially, we're just converting all the images into torch tensors efficiently. Okay. Okay, so now the advantage of this is that these little objects here should now be torch tensors. Add a few more cells. All right. We want to view the images probably, so let's make sure that we do have, in fact, images in there. So MNIST test tr.data, and we just grab image 423. We convert it to NumPy, and we view it. So as you can see, it is a handwritten tube. Okay? All right, so that's done. Then, so now for each tensor, we can make sure that we look at the shapes. All right, so MNIST train and MNIST test. So data.shape. All right, so we have 60,000 images, and the images are 28 by 28. And then we have 10,000 images for the test set. They're also 28 by 28. Okay, so we printed that. We're going to load them into the data loaders, the Torch data loaders. Batch size is going to be, I think, 1,000 is where I have it set currently. All right, so the data is loaded. Functions, these are just for printing the performance metrics, precision, recall, all that. And then this one, in case we want to plot something. Okay. So now let's take a look here. So we have, of course, these torch tensors. We need to convert them into sequences. So we actually have it in the right format, I think. So because this is just the batch size, right? We have 60,000. We have 28, that's the sequence, and then this is the vector. So permuting should be sufficient. So batch X has tensors 28 by 28, which need to be converted to a sequence. So reshape data to get 28 in sequence length, n batches, and 28 feature vectors. Yeah. So this is just, essentially we just have to permute it. And like I said, this permute feature is no longer necessary. They had created it like this, but I'm sure people in data science said, like, can't we just fix it? And so at some point, Torch did fix it. And I'm pretty sure it's just some kind of a flag where you say, like, true or something, and you can use the other approach. I just didn't look into updating it, but I know that that's the case now. All right, so here I'm gonna flip it just because that's how I have it set up. Sequence length is 28, size of vector 28, and the batch size. We permute, which will convert it into 28, comma, batch size, comma, 28. So you can see a batch of X will go in, and we just permute it by moving. So this should be 0, 1, 2, right? So by now saying 1, 0, 2, I have flipped those two positions. So that's essentially how it works. That's the function that I'm using here, or I will use. Okay. All right, so here comes the RNN network that we need to create, as you can see, because we have to make all the connections here, right? We have to put the fully connected layer and everything. So this is the, once we get through this architecture, everything else should be pretty straightforward. So let's go ahead. So I'm going to grab the whole thing, and then we're going to take out some things and add them back. Okay. So as you can see, we're creating, just like before, like we've done in 520 and in other examples, we're using, we always want to use object-oriented approaches to create our neural networks. So we create a class. I'm going to call it here MNIST RNNNet. We have our inherited class, if you remember. Okay. Let's look over here. So the RNN hidden state will be 128 neurons. So that's the size of the RNN hidden layer. So as I said, each one of these is of size 128. Okay? Remember, X times weights equals this one, right? So the same exact idea, just we're always using the fundamental matrix multiplication. We just have a different, algorithm, if you will, or a different configuration. And then classes is going to be 10, the total number of classes for MNIST digits. All right, so I usually like to kind of do it like this so that we can simplify it a little bit. And then dive deep. All right, so let's look at the class. So this class actually has 3 functions, as you can see. We've got our usual in itself. Yeah, it's good. All right, so we have our usual init class here, this one, the constructor, right? So we instantiate it. We have our usual forward class, but as you probably remember from the GPT, we can have more functions in here. In this case, we have a function for the init hidden. Remember, what is that? You need to have a thing here, right? So it can be zeros, random, but maybe the starting conditions are pretty important, right? So it could be that initial state is critical, right? As people, and people in dynamics and things like that. So when they created the architecture, they left that as an option, right? In our case, random or zeros. In most cases, random or zeros will work. Okay? So you can see that here then. So this will be for creating that. This is the initial hidden layer in time, and it's going to be all zeros. Okay? So that would be the vector going in here. All right, so let's start with the init function, the init first, and from there we're going to proceed. So let's add a few parameters. Okay, so n layers. You can see this one was tripping me up initially, but it is the number. It is in fact, you can see confirm here, is the number of hidden layers. All right, and that's why, and that's because this can be a deep neural network. Essentially, if you think about it, if I look at this configuration, it's not deep learning, right? It's just more like a multi-layer perceptron, because there's only this idea of one hidden layer, really. And then, yeah, there's these layers, but they actually represent different things in time. Where it would become deep is that there's that rolling effect, right? So that what I said before, actually there's between the x and the y, you can roll this out, right? And so those are the number of layers. But so that makes it deeper, okay? But here we're only using one, okay? And that was good enough. 128 is the size of the hidden dimension, so the size of each one of these is 128. Sequence length is 128, so we specify that because that's going to be the 28 steps, 1, 2, all the way to 28. And the size of vector is also 28. Each one of these is 28, which is like in the time series GPT was like 10 or something like that. So you can see that definitely both of these models can be applied. There's consistency. Okay? All right. All right, so we have this defined now. Okay, great. So that was easy enough. Now comes, if you notice, there isn't much in terms of an RNN, right? In terms of an RNN, it's like you just have to use your imagination and then you create the object. That's essentially it, because that's the whole thing right there. But you have to know what the values are. So I'm calling this one RNN1. It is an NN RNN, right? And you just have to know what each of these means, okay? That's important. So in this example, 1, right? So 1, number of hidden layers, we just have 1. We don't have 3 to make it deep. But you could. All right, the size of the hidden layer is 128. Notice I could have used the variables. I'm not, but it could have, because I want it to be very explicit when I look at these things. All right, so 128, and the numbers help me. So 128 is the size of the hidden layer. Size of vector, you can see, it's not the sequence, but the size of the input. So we're saying that we need to specify that this is 20, what size this is, what size this is, and how many layers, which makes sense because that works. Notice in the RNN we're not saying how many, the sequence length. That's not anywhere here, right? So just 28, 128, and 1. All right, that creates the RNN object. We will need the initial one, and then look at these. These are very simple and straightforward. We're very familiar with them already. Dropout, so you guys know what dropout is, right? So when we're training, we randomly don't use 25% of the connections in this case, right? And that, or 20%. And then we have our fully connected layer. So NN linear, so it goes from 128 to 10. So remember what I said here is just once I have this guy, this vector, this one vector of size 128, that goes into fully connected, so it goes from 128 to 10. And that's my head that I can use to predict. Okay? All right, so that, that's all the elements that we did before. now we just have, and that's all of them actually, now we just have to define the hidden state, and then in the forward, we bring the whole architecture together because we need to link this fully connected to this RNN1. Okay, so yeah, as you can see, that's done. Now let's take a look at this part here, the initial vector. So this guy goes in here. Okay, so initial hidden layer in time, which is all zeros. So you can see why is it all zeros, because this function, whenever I invoke init hidden, it returns a torch tensor that is all zeros. Maybe it's better to use random, I don't know, you have options. Notice here, once again, number of layers, 1, this is 1. Okay, batch size, it's necessary to provide the number of samples that you have, and 128 makes sense because it should match. If all of these are 128, it should also be 128. Got it? Just need, I don't know why that, like I said, the reason, essentially I think now there's a flag that says, hidden state can be inferred by the model, but I'm sure people wanted to experiment with that hidden state, thinking, okay, that's really important, okay, for some reason. Maybe there's also this idea of encoder and decoders with RNNs. So you have to think about it that way. You have a encoder part, and that produces a thing, and that becomes the input to the decoder. So you can see that there. Okay, so we have, so that's it, right? So we created our init hidden, so that's done, perfectly done. Then we look at the forward function now. So we're going to let's look at the first one. Okay, so XB comes in, right? The data comes in. What is the data? It should be 100, 28 by 28, right? That's our data, but we need to permute it, right? Because, as I said, I'm not using the flag. So I already defined this function, make image into sequence. I think. Yeah, here it is. And essentially all it's doing is it's flipping the batch size to here and the sequence length to here. That's all that's happening. Because that's how, in this particular setup, it's expecting. All right, so we did that. So now XB would be would be 28, 1000, 28. So then now here's the tricky part. It needs to go into we need to initialize the hidden state, so that's the next step, so that we can provide that for the RNN. So that's going to be self.initHidden. So essentially it creates this vector here, right? And that's the initial hidden state. We call it self-hidden, and that needs to be plugged into the RNN. So that's going to be this next part. Notice here, this is like all the work right here, right? So okay, so let's see. Self.hidden now contains, so this is saying this here, which I already explained, will contain the final information, right, of everything. Self-hidden now contains the final hidden state, which captures everything for each image in the batch. So notice how it works then. We've already defined RNN1, this guy over here, essentially the whole network. And we need to provide to it, what do we provide to it? Batch X sequence, which is this one. That's just the data after the permutation. And we also provide that hidden state. Do you guys see that? That's it. And so RNN then returns, as we saw, RNN-O or self-hidden. And we can ignore the dropout for now. So as we discussed already, RNNO, what did that return? The entire sequence of H's, right? So we just saw that before when we were looking at the metrics. So it gives you all that. And it also sort of returns this parameter and then self-hidden, right? And self-hidden now will have, it's like a convenient way, right? Because this also contains it. It's just the last one. So here we have the whole sequence. We can grab the last one, or this one conveniently gives you the last one. Okay? What I'm saying is it gives you this one, H28. So now you take, so did that make sense, guys, for everyone? Is this clear? Everyone good? All right. So yeah, so essentially we're done, right? So that's the whole game. So now we're just going to run that self-hidden through a dropout, or this is not being used. So I'm gonna grab this one here. Notice that it's not being used. And so I grab self-hidden. So as I'm making a prediction, so think about it this way, right? So I'm gonna have a loop, and I'm gonna be giving it batches. The batches will go into the RNN. It'll produce self-hidden, then self-hidden goes through the fully connected, and boom, it predicts something. That is going to be compared to the real, and then it back propagates in the network. And that's it. All right, so I give it self-hidden. Okay, so now this self-hidden, the last in the sequence, goes into my fully connected. What is my fully connected? It expects a vector of size 128, and it does a matrix multiplication to produce a vector of 10. Okay, so that's essentially this part. That should produce something. So I didn't copy the whole thing. Yeah, I didn't. So I need to obviously produce out. There. So I have my out. Okay, so now it's a vectors of 10. And this then, we just reshape it. So out view. So it infers batch size and classes. So it'll probably be like 1, comma something, so it's just getting rid of that. All right, and so now I have my Y-preds, which are the things that I'm predicting. All right, so that should be, oh, and then of course we need to return Y-pred. So I'm going to return Y-pred, and that should be it, right? So that's the whole architecture of an RNN for this particular case. Now we have our train loop, which is, should be the same thing we always use. From train DL, we grab XB, YB, squeeze it in case there's some issue with dimensions. So we've got XB goes into the model. It predicts Y-pred. So essentially data feeds into here, goes through all of this, but we only grab this one. And then that one we apply the head from 128 to 10, makes the prediction, and that's it. So then this Y-pred is compared to YB, and that gives us our loss. And now we optimize. So there we are. Oh, that's the function. So now we can go in. Whoops. All right, so we instantiate the RNN net. We're going to use cross entropy for this one. Notice I'm not using anything like softmax or anything, and that's how a J likes it, right? Right, so loss FN apparently has a softmax built in, something like that. All right, so we have a cross entropy, then torch atom optimizer. We map the parameters, right? So it's the exact same thing we would use for anything else. So let's go ahead and run it. Should I use a GPU on this one? What do you guys think? Should I use a GPU on this one?
Sequential.
Sequential, right? So there might be efficiencies in using, the GPU, but it's not really designed for that. Do you see what I'm saying?
Are there any gains as it gets further, I guess, like in your diagram to the right, where it's got all the earlier layers and can it propagate?
Say
upward
that
and
again.
outward?
What do you mean?
So like the X's, all
The
they're all
X's.
sequential,
Uh-huh.
but like you should be able, by the time you get to X3, you should be able to compute like H1, H2, H3.
Yeah, I could grab H3. Yeah,
And then continue going. up to
we
the
can
left.
grab H3.
Does the GPU help much with that?
Oh, so in terms of GPU, you mean?
Yeah, because I mean a lot of.
What do you mean, like breaking it up or something?
Well, I'm just thinking like the upper left corner, it probably won't be ready to do any operations with early on.
Mm-hmm.
But the way that the layers are connected later on, like right at the very end, it should be able to do almost everything, right?
Yeah, if you're here. So are you saying just skip like a few towards the end and just?
Yeah, I don't know. I mean, I guess it wastes power and cycles on GPU, but is it faster than CPUs though?
I think it might be a little bit faster just because of how it works, but like the transformer, right, is made for a GPU in theory, like in
Yeah.
terms of design. Like I've said this, it doesn't have these blue little connections. That's one way of thinking about it.
Yeah.
Everything, like the sequence is contained here. So the way to think about it is instead of this, there would be a vector that says 0, and then a vector that says 1. So because this one depends in theory from the previous one, right? You agree?
Yeah, but would it be able to do the computation for H1 and X2 at the same time?
H1 and H2 at the same
Well,
time?
H1 and X2, I mean.
This needs to finish first before it can do this. Because
Yeah.
this is, H1 times weights equals H2. So how can it get H2 if it doesn't have H, like that? That's a matrix
Yeah,
multiplication
but
too.
can't do all that quickly.
Might be able to do it, quickly, but it's still in sequence.
Okay.
What's different with the transformer is it should be in parallel, right? It should be
Yeah.
like in parallel. So that's kind of the point. This is why RNNs were defeated. I mean, it might be like a beautiful architecture, right? But it had actually an inherent problem that this guy here, H5, is H4 times W equal H5. And this H4 is H3 times W equal H4. So it needs that. And the back propagation also needs to happen, right? So think about that one.
Yeah.
So if we're going in reverse, this predicts 10, then now we back propagate to this guy, then this needs to be back propagating because all these weights need to be updated. These weights also need to be updated, right? The ones that go from X to W and so on. You see, so in essence, it should be a bit slower in theory. Okay, and that's really why it was defeated, I think. I mean, because they've actually put attention into an RNN.
Yeah.
Like somebody came in and grabbed an RNN and slapped attention to it, LSTM. So they can put a lot of the elements, right, of a GPT into an RNN, but they still can't make it parallel because of the sequencing. That's the fundamental issue. So let's see, how many epochs are we doing? Huh? 20? Okay. All right, so we're almost done then. And then we'll finish with this here, call it, you guys are RNN experts, and we'll move on to something else. All right. If you want, what I was going to suggest is that I could give a bonus homework. If you want to take your time series data and want to challenge, right, and implement it to the RNN. So if you do that, I will give you a full bonus homework. Okay, but I'm not. It's just we're too tight on time to distract you with that because I want you to work on the project and other things. Got it? All right. So just keep that in mind. All right. So I think it finished. Okay. So that's the check, the green check, and let's just evaluate performance, which should just be this line of code here. And I think actually, let me actually do this one because I think this is better. It's not defined. What? Okay. Okay. Yeah, I needed to run this, I think. All right, so it's printing, just giving the results. They all look good, basically. Okay, it finished that. So they all look good just by the diagonals. And then I'll just do this one. But yeah, so we can see it runs pretty well. Yeah. So that's probably the last one. All right, yeah, so that's it as far as RNN. So that concludes the discussion on RNN. So in conclusion, we looked at this architecture. We don't really have to define anything, to be honest, as far as the network itself. It's all internal, but we have to know what the values are, right? Where to plug in, the meaning of the values, and then the key insight is you get either the sequence of the hidden states, or you just get the last one. And then in the key aspect is when we're building the class, we have to take either all of this or all of this and add a specific type of a head, right, that we can use. And then we get predictions that comes out as ypred, and then in the loss function, those predictions are compared to something real, and we backpropagate. All right, that's it. All right, guys, so I'm going to end the video here. This concludes our recurrent neural network.